Hello everyone, welcome to Tech-Lavya. Please like, share and subscribe.
Now in last lecture under electrical machines, we discussed the constructional details of induction motor, three-phase induction motor to be precise, and we also discussed two types of induction motor, which are squirrel cage induction motor and face wound or slip ring induction motor, isn't it? And we also compared these types. Fine. Now today we are going to discuss the phenomenon which is responsible for the principle of operation, like how that rotor rotates. Okay. So basically this RMF, which is rotating magnetic field, is responsible for induction motor's operation. As in, the basic job of motor is to convert electrical energy into mechanical energy, right? So the rotor which is inside that induction motor actually rotates. So it actually converts electrical energy into mechanical energy. So this rotating magnetic field is responsible for that mechanism, or that effect. So today's topic is going to be very important for your concept clearing as well as for the exam sake. Fine. And then after understanding the rotating magnetic field, then we'll be talking about how does an induction motor, three-phase induction motor, operate. Okay. This. Fine. So first of all, let us talk about rotating magnetic field. Now, what is the structure of induction motor? It has a stator which is stationary, and inside it you have stampings, and in those slots or stampings windings are put, right? We are talking about the three-phase induction motor. So the windings carry three-phase supply. Okay. Then in between you have a rotor, and as we said that the electrical supply is given to the windings which are placed inside the stator, and rotor receives the magnetic field by induction. Fine. So there has to be something which is responsible for the movement of this rotor, right? So basically, how does this rotor starts rotating? So for this, rotating magnetic field is very important. Okay. Otherwise, my rotor will not rotate. Okay. So basically, when three-phase supply is used to energize three-phase windings, the flux also rotates in space around the stator synchronously. Synchronously means in a uniform speed. Fine. So there can be two ways. Okay, one way is shown on the right hand side. It contains a rotating frame. Now see, what is the difference? Now we said that stator is basically stationary part, right? But then in this case, what are we going to do is, we are going to rotate the frame. Okay, so we will rotate the frame, and that frame contains the winding. Okay, and because of that winding, magnetic field is produced. So when you start rotating the frame, it means that magnetic field will also rotate. Okay, because see, what do we want? We want that magnetic field to be induced inside the rotor, and we want this magnetic field to interfere with the original magnetic field, and in turn we require the torque to be produced. Okay, so the first magnetic field should change. Okay, so either the magnetic field can rotate or the magnet itself can rotate. So what we are doing is, in this case, we are trying to rotate the magnet. Okay, so what we are doing is, we are rotating the frame itself. So obviously when the frame rotates, the magnetic field also rotates. Now how this frame is rotated? It is rotated by using some engine at some specific speed. And the frame has four poles. Okay, and these four poles are shown here. So this is north, south, north, south. So these are alternate poles. Fine, and we will rotate this. Okay, so this is one assembly. Now this is one assembly and this is another assembly. Fine, but do you feel that this is feasible? No, it is not. Okay, so we will talk about another type, because we don't want to rotate the frame, because for rotating the frame we require a separate engine. Okay, so this is not a feasible method. So what is another method? Another method is to rotate the magnetic field. Why to rotate the frame? So there is one more way to produce rotating magnetic field. So here the stator is fed with three-phase supply. So it is shown here. See, you have R, you have R, Y and B, three-phase supply, and this is connected in star fashion. Okay, so these windings are three-phase windings and they are supplied with three-phase supply. Okay, so these slots are connected in star or delta. Basically star is preferred, but if you wish you can connect it in delta also. Okay, now what happens? Now suppose the winding is wound for 4 poles. Okay, it means if the windings are wound for 4 poles, then stator acts as 4 poles. As it was shown, it had 4 poles, so stator also acts as 4 poles. So when three-phase supply is given, it produces rotating magnetic field. And the speed at which the magnetic field rotates is called the synchronous speed. Now this line is very important line. That what do you mean by synchronous speed? It is the speed at which the magnetic field rotates. Okay, please remember the speed at which the magnetic field rotates. Okay, and that synchronous speed is given by ns 120 equal to 120 f by p, where f is the frequency and p will be the winding is wound for p number of poles. So we can calculate the synchronous speed, or by changing this f and p we can change the synchronous speed. Now obviously this method is preferred because here the frame and windings are stationary. Okay, so how this rotating magnetic field is produced? So see, this is how actually the arrangement looks like. So here you have 6 slots. Okay, so you have R1, you have R2. Fine. So in three-phase supply, what do you have? You have R conductor like this, correct? This is R conductor. Then perpendicular to this, you have Y and B conductor, and they are placed at 120 degrees from each other. So these are B, and then you have Y conductor. Okay, so R1, R2, Y1, Y2 and B1, B2 are shown in the figure. Fine. Okay, now see, three-phase supply is given to this R, Y and B, and they are star connected. Now when the three-phase supplies when the three-phase current flows inside this conductor, what happens? When the three-phase current flows inside these windings, then suppose this R1 becomes north pole, then R2 automatically becomes south pole. Okay, now I want to take yellow, but I don't think that it would be visible, so rather I would prefer some other color. So let me take this. So again this becomes north, so this becomes south. Okay, if this becomes north, then this becomes south. So basically what I wish to share is that one terminal becomes the north pole and another terminal becomes the south pole. Okay, So stator is shown below. It has 6 slots, R1, R2, Y1, Y2, B1, B2. 6 slots. And it is wound for 2 poles. So you have 3-phase supplies. Okay, you have 2 poles. So what is the distribution? Distribution is 1 slot per pole. North pole, south pole. So 1 slot per pole per phase. Correct? So per slot per pole per phase means what? That R1 acts as north pole, R2 acts as south pole. Correct? So 1 slot per pole per phase. And these slots will carry 3 coils, and each coil has 3 terminals, and R1 represents start and R2 represents finish. It means the current starts at R1 and ends at R2. Okay? Yes, and this is given to 3-phase supply. Fine. So this is how it is actually shown. So we need to understand now this diagram. Okay, so before going to this diagram, I want to explain this whole concept in a very simple manner. Okay, please pay attention here. Now suppose you have a stator here. Okay, so this is a stator. Okay, now here you have north, south. Okay, then you have again north, here you have south. So next you have here north, and here you have south, and inside you have rotor. So automatically, because of this magnetic field, because of the magnetic field produced in the stator, in rotor also magnetic field is induced. So here north pole, here also north pole is formed. Because of this north pole, again here north pole is formed. So similarly, it also forms north and south pole. But what happens? This north and this north will repel each other. So this north pole, okay, now this north pole will repel from the above north pole, and it actually wants to go towards south, because we know that similar poles repel each other and dissimilar poles attract each other. So this north pole wants to go to south pole. Okay, correct? So it tries to catch up the south pole, and in this process it starts rotating. In this process the torque is produced. Okay, but what happens is, this is a 3-phase supply. So in 3-phase supply, continuously the phase is changing, because here you have such kind of signal, right? So what happens? Yes, continuously the magnitude is changing. So this, see, okay, so now let us see what happens in the next cycle. Okay, now this north pole shifts here, correct? So this is north, and now this becomes south. So you have north like this, and now you have south pole, correct? Because the supply is continuously changing. So see, it is rotating in this direction, correct? So see, it means that the rotor north pole is trying to chase the south pole of the stator, but south pole of the stator is also running, correct? So let us see what happens after some time. Again this south pole comes here now, correct? So here you have south, south and south, and north pole has rotated, it has moved. Now understood, this is called rotating magnetic field. Okay, so this is how actually magnetic field is rotating. Correct? It means that rotor is actually trying to chase the stator, but it does not succeed. And in that process, it starts rotating. Understood? So basically, this was the phenomena. Now, with the help of proper diagram, we will be talking about this. Now, I tried to explain it in very simple language. Okay. Now, this is the phenomena. Fine. Yes. So, what we will do is, we will mark few points. Now, suppose this point is A. Okay. Then this point is B. Fine. Sorry. And this, yes. And this point is C. Just for our reference purpose. So this denotes A, B and C. Okay. Yes. So now we will be talking about A condition. So what is A condition? In A condition, your, I shall be using some other color pen. See, this signal is maximum, isn't it? So this is maximum here. Okay. So this R, see, this R1 is cross. Cross means what? It is going, the current is going inside the screen or inside the paper. Okay. Now you are aware of the right hand rule or screw rule. So just keep your hands such that your thumb is outside. I mean, it is coming towards you. It is facing you. Okay. But then for cross, it has to go inside the screen. So, you have to pose as in you are pressing a dislike button. Don't do that. I know you like it. But just for the sake of understanding, you have to keep your hands as in you are saying, no, I dislike it. Okay. So it is moving inside the screen. So your other fingers, they represent the field. Correct? So if if the field is going inside the paper, it means this is the magnetic field direction. Right? Okay. Similarly, so for R1, B2 and Y2, the current is going inside the conductor. And for Y1, R2 and B1, current is coming from the conductor. Okay, it is coming from the screen, from the paper. So now you can say, yes, I like it. So when you say I like it, see what is the direction of your fingers. Thumb is like you are showing thumbs up. Correct? I like it. So your other fingers are showing the direction of the magnetic field, which is in this direction. Okay, so this assembly shows that it is in clockwise direction, whereas this assembly shows that it is in anti-clockwise direction. But in turn, the magnetic field is moving from right to left, isn't it? So magnetic field always travels from north to south. So my right hand side becomes the north pole and left hand side becomes the south pole. Understood this phenomena? Yes. Okay. Yes. So let us move to the second part. Oh, by mistake, I did this. Doesn't matter. So this was the thing. Okay. So now we will talk about this. Slightly it has moved ahead. But you can see that another signal this particular signal has reached 0 here. Okay, fine. So this y1 becomes 0. See, this y1 has become 0. Correct? Yes. So now y1 and y2 behave as 0. So your magnetic field is at R1 B2 and R2 B1. Again you can see that the direction of magnetic field is from this direction to this direction, isn't it? So this is North Pole and this is South Pole, right? So earlier, see, North Pole was here, South Pole was here. Now it has tilted a bit, isn't it? Right? Next, again erase all. Now again we will be showing the next scenario, this scenario. So in this scenario, two signals are, why I am doing this? Yes, see, these two signals are positive, right? But this signal is negative. So your R1, B2 and Y1. Here the current is going inside the screen, inside the paper. Okay? Understood? Yes. But for B1 it is still negative, right? So it is coming outside the screen or outside the paper. So again you use the right hand rule. Again you will understand that here these three form the magnetic field in this direction, okay, clockwise direction. Again you notice that these three make it in the anti-clockwise direction. Sorry, I made it. Yes. So it is in anti-clockwise direction. But if you notice the direction, it is same, so it goes from North Pole to South Pole. Now see, in the first case, North and South were like this. In the second case, North and South Pole are like this, correct? And in the third case, again, it has rotated. So continuously at various instances, this is North and South I'm talking about, yes. So at various instances, continuously the direction of magnetic field is changing. So this is how rotating magnetic field is produced. Okay, and this rotor wants to chase. Rotor wants to chase this magnetic field, but it does not succeed. In fact, the induction motor operates because the rotor can never catch up the stator. Please try to understand, the moment rotor catches the stator, your motor would stop. Why? In that case, it would be locking condition. You know, we talked about locking condition in earlier lecture, right? So basically, your induction motor will operate as long as rotor is chasing the stator. Got it? So as soon as it actually chases, the motor stops working. So here again I arrive at some conclusion. What conclusion? You have now synchronous speed. Now what was synchronous speed? Synchronous speed was the speed of the magnetic field rotation. And now you have one more speed. Synchronous speed was represented as ns. Now you have one more speed, which is n, and that n is the speed of the rotor. So what do you feel? What do you feel? What should be the relationship between this n and ns? Should it be greater or lesser or equal? Yes. Come on. Ns should be always greater than n. Or in other words, the speed of the rotor should be always smaller than stator. Or of course, stator as in the stator is not rotating. Synchronous speed I should say. Right? Unless and until this, see, till this condition is satisfied, my motor is working. Okay, please keep these small things in your mind. Okay, yes. So I hope till this point many things are clear to you. Okay, so now here one more scenario is shown. So basically you have the stator here. So you have the stator, you have the rotor, and the magnetic field is coming in this direction. Okay, see, this is the direction of the magnetic field. Fine. So here is my rotor. So rotor is getting the magnetic field. Okay, yes. So now, till now we used right hand rule. Now we are going to use Fleming's left hand rule. Okay, so what do we do in Fleming's left hand rule? In Fleming's left hand rule, you have your thumb, you have your index finger, correct? Your index finger represents current, okay? Then the middle finger represents the force, and your thumb represents magnetic field. Okay, so this is index finger, okay, and this is thumb. Obviously the third one is the middle finger. Okay, yes. So please arrange your left hand so that you can. So now what you have to do, magnetic field is your thumb, right? So what you have to do is you have to arrange your thumb so that it shows the direction of the magnetic field. Okay, so I would just give you a hint that thumb should face you, correct? It is going, the thumb is facing you because it is showing the direction of the magnetic field. See, it is coming in this direction. Now the current direction. The current direction is shown by the index finger. Okay, the current direction is shown by the index finger. So where is the current direction? Yes, where is the current direction? Come on, current direction is dot. See, here it is dot. So what does dot mean? That it is coming out of the screen. Now you have to slightly tilt your hand so that your index finger points you. Your index finger points you. So the thumb goes down. Okay, the thumb goes down and index finger points you. Now where does your middle finger points to? To the right hand side, isn't it? Correct? So this is how, see? Okay. So have you got this? I hope you have. So this is how it rotates. So continuously the magnetic field direction is rotating. So rotor also starts rotating. Got it? Fine. Now we were talking about the speed of the rotor and synchronous speed. Fine. So I told you that synchronous speed should be always more, or I told you that the speed of the rotor should be less. Correct? So actually In other words, I can say that the rotor slips the synchronous speed. Okay, see, we are talking about synchronous speed, but induction motor comes under a synchronous motor, because the time it becomes a synchronous motor, it will stop, working. So it comes under a synchronous motor. Now I was talking about slip. So what is this phenomena slip? Slip is the phenomena wherein your rotor slips the synchronous speed, or the difference between the synchronous speed and the actual speed of the rotor is known as slip. Okay, so numerically I can say that this is slip. The difference between the synchronous speed and the actual speed of the rotor is called slip. But then percentage slip, if it is calculated percentage wise, then it is represented by ns minus n upon ns into 100. Okay, fine. I hope this is clear to you. So this was all about three-phase induction motor. We shall be meeting with single-phase induction motor. Till then, keep studying.